We are in the middle of chapter 12 on eligibility traces, and the purpose of this chapter is to sort of generalize techniques that we had previously in the book, which are these n-step techniques where we're looking forward at an agent interacting with the environment, and there's this idea of we don't actually know what this target, what this return value is, this discounted future return, until we see all of the future rewards. And of course, like for some problems, that will never happen because the future rewards will go on for infinity. So we really, like this discount rate will end up making it so only up to some time horizon do they actually matter. But for an episodic task, we would generally have to wait until the end of an episode to see this whole sequence of rewards. But an alternative to that is to use bootstrapping to, look at a sequence of rewards up to a certain point, like here, some number of steps n, and then use some existing approximation value that will get better over time. So like initially this approximation will not be accurate, but the idea is once this algorithm converges, then this will all be correct, and this bootstrap value will be a stand-in for all, like what would be all the future reward samples we would collect. So previously we had different options, like we could either look at like the TD0 algorithm we had where we just looked at like a single step forward here, and then we also had in the other extreme case, like here this is showing that this like gray box represents a terminal state. So when we use like the Monte Carlo sampling technique, then we had actually sampled like all of the steps all the way out to termination and then use that value. With the lambda return, the idea is that we're actually going to use all of the different n-step returns, but they're all like weighted by some different value. And this is what I showed last time, where depending on the value of lambda that you pick and the steps till termination, it affects how much weight is placed on each of these. Now, this particular way of weighting the n-step returns, where the shortest return is weighted by 1 minus lambda, and then there's just a value of lambda to the n multiplied by each one, so it decays out. Like the higher the value of lambda, or the closer lambda is to 1, then the more evenly all the returns get weighted. And in the extreme case of lambda is exactly equal to 1, you end up getting, all of this is where there's like a terminal state here, but depending on wherever you terminate, it doesn't really matter in this case, because when lambda is actually 1, you place all the weight on, on the Monte Carlo return. But then any value less than that, if I send these steps till termination out very far, you just see like you end up getting all these returns are weighted, but the drop off, like the decay rate of the returns from the shortest possible option of TD0 out to here becomes more extreme as lambda gets small. And in the extreme case of lambda is 0, we end up getting all of the weight on this initial, this should actually, there's this diagram in the book where, yeah, it shows, sorry, this should be one sort of sequence shorter, but this is like the TD0 return, where we just look at a single transition into the future and then use the value estimate here. So we had compared the TD lambda return to the n-step methods. This is on this random walk task, and this is all what we went over at the last meeting. When we did those exercises. And this the purpose of this toy problem, the random walk task, was just to show that there's some intermediate value of lambda which generally converges faster. So this is showing like this is a task where the true values are very easy to calculate. So these curves represent the error between the true values and the values that are being estimated using this, this TD lambda algorithm, where here, the target value being used here is the lambda return. This happens to be like, this is a tabular problem. So the function approximation and gradient here is just, it's trivial. Like this is just the parameter that represents one of the states in the problem. This gradient's always one. So only a single parameter value gets updated at each step. But this was just showing that this lambda return is just a different way of doing these sort of different n-step methods. And we don't really know ahead of time which, is it better to use like a particular value of n, like n equals 4, or lambda is 0.8 represents some mix of these n values where like the weight will always be highest on n equals 1, but then there'll be like other of these returns will be included. But you could see here like the performance, at least for this problem, is about the same between like the best value of n and what seems to be the best value of lambda here. So it seems like to actually do this, to calculate like this lambda return, you need to have a calculation of each of these sequences, and like you have to go through this trajectory up to a certain point and repeat a lot of steps. But it turns out that there's like this weight update, you notice, just happens once every step. And this is like assuming we know this target value. Oh, sorry, I'm just going to mute you, Marcus. I don't know. But if you do want to introduce yourself or say something, you can type a message in the chat. So yeah. So with the TD lambda algorithm, we'd introduced this concept of an eligibility trace. And what this vector does, like this vector will have the same shape as whatever the parameter vector we have, where like these are the parameters we're using for function approximation. And it turns out that if we keep track of this eligibility trace, then we can update it once every time step. And then we can use it to update the parameters where now, instead of the gradient appearing here, where this, delta target is, like this delta, this is the same target we had seen before with all the other TD methods. This is just the TD error at a particular time step. Right, but now here, this would normally have the gradient. And now instead, we're accumulating gradients in the eligibility trace vector. And then the weight update uses the eligibility trace vector. It's the update. And with this method, we can just update this once every time step and the parameters once every time step. And we don't have to keep, going back through and calculating all of the n-step return values separately. And there is an exercise. So the claim is that with this TD lambda algorithm, like by the time we finish, we get to the end of an episode, then it will have performed all the updates that the offline lambda return algorithm would have done, where, this is the offline lambda return algorithm where we actually use like this, like the gradient and the target value of G each time. But you see, like, it appears that this calculation of the lambda return, like, requires us to, perform this sum you know, and do this like, I mean, well, first of all, like this value of the lambda return, we won't even know it until we reach the end, like the terminal state of an episode, right? Because in general, like we have to do this weighted sum all the way out here. So what we can do is imagine like reaching the end of the episode, like where we have this entire trajectory, and then we can sort of go back through and calculate all of the lambda returns, um, where you know we're going to need to have. I mean, I'm sorry. There's only one lambda return, but using all of these, you know, n step returns, we're going to have a separate n step return depending on how long the episode is. But you know, the point of the TD lambda algorithm is that you know we don't have to wait until the end of an episode. We actually do these weight updates um, at every step of the algorithm, and then the claim is that by the end of all these updates here, that you know we will have updated the parameters the same way that the offline algorithm updates them, the offline lambda return. And there is an exercise that is designed to show this. It's exercise 12.3, and I think we had skipped, or we had sort of ended last time at the end of covering TD lambda. And you know, this, I think a good way to like finish summarizing it is to show this exercise. Like it isn't actually that difficult, although it's always a little hard to go through this math, um, you know, with people like following along. But you know, you can find this in your notes, the cell, yourself in the notes. But the point of this exercise is to show how something that is in the TD lambda algorithm, or so like something that is part of the offline lambda return, can be written in terms of something that's available at every time step, which in this case is the TD error at every step, right? So the lambda return for G, like the actual expression for this, is here, right? Where this quantity is the discounted return, you know, up to this time step, right? So we have like, there's a lot of nested quantities here being computed. Like this itself is a sum of rewards. And then in here, we have a sum of these that are being computed, right? And so in order to perform the offline lambda return algorithm, we need to have this error term at every step. And when we do the TD lambda algorithm, instead, we end up using just the one-step TD error at every time step, right? Which is represented here, right? And this is just the bootstrap value at the next step, right? This is the reward we get from taking this step. And then the discounted value at the transition state. And it's the difference between that, which is like, this is the TD0 value estimate. And then this is the current value estimate at the state we started in. So the the question in this exercise is there a way to express this, right, to express the lambda return or this error term in terms of the TD errors? And also there was this also makes use of this previous exercise, which I think is yeah, and this we did go over last time. But in this previous exercise, we had derived this recursive expression for the lambda return, which is another, you know, important step in writing this. But throughout this book, there's a pattern of deriving recursive expressions for different quantities. So, you know, the lambda return, if you look at it here, is written in terms of the sum of these n-step returns. And at the end of this exercise, 12.1, we had derived that we can actually write the lambda return as a function of the lambda return at the next time step, right? Or you could invert this and get, the lambda return at a future time step in terms of the one at a previous time step. Okay, so we do need to have already completed this calculation. Here, I'll go back to this exercise 12.3. So here is the recursive relationship for the lambda return. And then I'm going to call, this is the error term that we need for the offline algorithm. So I'm just going to call it, this here. I'm just going to designate it as VE, or like the value error that we're using for this problem. So in order to derive this, you can first exploit this recursive relationship, right? And here I'm just replacing the lambda return with the recursive relationship. So we get this now G at the next time step. And then you can regroup some terms, but you notice that the reason why I have grouped the terms like this is so that now this portion of the expression is actually just the TD error. Right, see? So this is like the one-step TD error here, where we just have, in terms of the bootstrap value at s of t plus 1 and the reward here. So now at least, we've replaced part of the expression with the TD error. And then, you can see that now what's left of the expression, if you compare it to the starting thing here, is all of the t values are just incremented by t plus 1, right? So actually, like this, we can already see that we can now keep extending this recursion out, right? And we can then replace this term in the brackets, right, with the value error t plus 1, because that's what it is. And then we already have this one recursive expression. And then we can see how this expands out, and we can keep stepping it forward in terms of the next iteration of the TD error, right? So if the task is continuing, we don't have to worry about the terminal state, which makes things a little messy. We can already just immediately write this error term as this sum of TD errors, right? Because here we just have this factor of gamma lambda to the nth power. And then, you can see this is just going to expand out into a sum of all the TD errors. So that should give some intuition that it is at least possible to compute all these updates of the lambda return only using the TD error, which is done. And then the next exercise, which is probably a little too involved to go through the whole thing here, but this is to actually directly show that if we do all of these weight updates of the TD lambda algorithm, which involves updating the eligibility trace here and then updating the parameters, that we end up doing the exact same updates that we would do with the offline lambda return. Where again, the offline lambda return algorithm is given here in 12.4, where a lot of the complexity is hidden away in the lambda return value. So in order to show this, you have to it's pretty tedious, but you have to go through all of the updates of the eligibility trace and the weight vector update, which is what I'm doing here, and sort of keeping track of all the numbered states that we're going through. And you end up, noticing certain patterns, but yeah, so here, one of the steps you have to do is group the terms in terms of the coefficient of the TD error. And then once you do that, here, in the next part of this exercise, these are the offline lambda return weight updates. But yeah, I won't go through the whole thing here. But the point of these two exercises is to show that this much more efficient TD lambda algorithm, under some assumptions, like this is assuming that the weights don't update during an episode, which you could completely do. Typically, we don't have a separate copy of the weights that we keep fixed. We'll update them during the episode. This proof just is easier if you do that. But in a limiting case, this TD lambda algorithm will reproduce all the update steps of the offline algorithm. But we can do it in an online fashion, which means we can also do it for continuing problems where the episode never terminates. We'll have sort of an intermediate result, but in the long-term limit, it will approach what the offline algorithm like would be if you were able to continue it out to termination. So, then I have implemented it in here. Sorry, so this is sort of a recreation of this same diagram here. It's not actually written out in the book, but here I have this implementation, all right, of the offline lambda return algorithm. And in order to implement this, I did, make use of the recursive result of the lambda return. So inside of this algorithm, this, sort of goes through the episode backwards, like we did for some of the tabular methods, and it keeps track of the lambda return at each step, starting at the terminal state, if there is one. But yeah, this algorithm really like it only works if an episode actually terminates. If you compare it to then the TD lambda algorithm, I have these arguments here that either define where it runs for a certain maximum number of episodes or maximum number of steps. And then within this, like if a terminal state is reached, which is represented here, then certain things are reset. But this algorithm also works perfectly fine if you never reach a terminal state. Yeah, and this is also, yeah, for generic function approximation. So there's a gradient term here, but for most of the examples in this book, we're going to consider the case of linear function approximation, where we have some weight vector, and then we have some function which maps the states to a feature vector of states. So there's some fixed dimension of the feature vector, and which is the same length as the length of the parameter vector. And then the value estimate is just the inner product of the parameter vector and the feature vector. The gradient here, it just is very simple. It is always just the same as the feature vector in linear function approximation. So it just makes, yeah, here, like, so in this version, if this is for a linear problem, then, this just represents, that inner product I showed, and then the gradient here will always just be the same as the feature vector. So that's what's being shown here. I'm sorry. In the linear version of the problem, the only thing you need to define is, the number of parameters, and then a function that updates the state representation. And then here, the value estimate, like I said, is just this dot product. And then, the gradient is just equivalent to whatever the feature vector is. Yeah, and also, all the tabular problems from part 1 of the book are just a trivial case of function approximation. Like, here is an example of if you really had a tabular problem, you would just have all of the parameters, like to D. These would just be 1 for each state. And then, right, all of the gradients are just trivial, like one hot vectors where there's just a value of 1 for the state that you're considering. But you don't actually have to form these vectors. If you're actually dealing with a tabular problem, you don't need to really keep track of the gradient. You can actually just return whatever this index is, and you can just represent the states by a state index and forego that. We'll see later in the chapter where there is this certain type of linear approximation where instead of having like a general feature vector, all of the features are actually binary features. So here, like this is also a case of binary features, but there's only one feature per state. In general, you could have, you could use this for a non-tabular problem, and you would just have, some function that tells you which features are active for a given state. And then you could just use those sets of indices rather than actually needing to, fill these vectors out because they're going to be very sparse vectors. And generally, if you have these really sparse vectors, you don't actually need to represent the whole vector. You just need to keep track of the non-zero elements. So yeah, again, like this diagram, this just shows, this sort of confirms that you can see like the results of TD lambda look very similar to the offline lambda return. I mean, in the book, they do look even closer, or like the minimum. I'm not sure why in mine the error minimum is a little different, but it's probably just a case of sampling error here. Like if I ran this again, it might, but it's quite close. Yeah. So yeah, and we had gone through these two exercises. Okay, so these show the equivalence of the two algorithms. So fine. We know that, this return, right, like the TD lambda or the offline lambda return, like it really only is defined for an episode, right? Because otherwise we'll never actually finish computing it. Because you can see here, like in the little block diagram that shows how TD lambda works, this is assuming, there is some termination to the episode. So we have a finite number of these n-step returns. But we're also interested in solving continuing problems. So we come to this other concept, which is again, we're sort of layering now even more ideas together, but this is the n-step truncated lambda return, which is kind of a mouthful. But now the idea is that, let's say that, we have some episode where maybe it doesn't terminate, but we're considering some value of n, where now n could be smaller than the terminal state. Or here n is like the number, yeah. So where, if we look forward n steps, we may not have reached the terminal state yet. And if that is the case, then we're going to truncate the lambda return, right? So that we're only going to consider these n-step returns out to some time horizon h. Now, if it turns out that the episode terminates prior to that, then this will be equivalent to the lambda return, like because the truncation will have no effect. But it does have an effect in the case where, our truncation horizon cuts it off before we've finished. Right. So now we're kind of back. I mean, the important thing here is just, the only difference between this and the lambda return here is just that, we could truncate this at some earlier point. Like here, if we truncated it at 3, then we would only consider, these first 3 lambda returns where we have to use bootstrapping. And if the truncation prevents us from reaching the terminal state, then, we won't actually have this terminal transition to use. And like every single one of these values will have to make use of bootstrapping at this, this final non-terminal state. So this is a new algorithm where, where this is called the truncated TD lambda algorithm. And there is another exercise which is even more tedious math, which is to show that you can also write the truncated lambda return, or this target value of the truncated TD lambda algorithm as a sum of TD errors. And you can do it. Again, it's the kind of thing where it's probably better to try to derive it yourself, or you can go through this derivation in my notes later. But yeah, the final result is yes, you can in fact show that there's a way of doing this, which also means that there is some way of computing this target value incrementally, where we can do it on every step, and we don't have to wait until we reach, like the final, like the nth step. In the nth step methods we had developed in the first part of the book, we had to wait until we had gone n steps before we had the nth step return from the starting step. But here we have a way of updating it on every step, or at least that's what we're going to end up deriving as this true online lambda return algorithm. But the final algorithm here, which covers the case of state value estimation, is an online algorithm. So all the updates happen incrementally. We can do it. We can do one step. We can do the parameter update on every step of the episode, or of the trajectory. Is that incremental update will end up computing this n-step truncated target, or like these updates, without having to actually have this value computed on every step. And it's going to use eligibility traces again. There's this derivation here of these updates. Now this algorithm, which is very efficient, actually requires that we are using linear function approximation. So you can see here for the weight update that we have this inner product of the weight vector and the feature vector for the state at time step t. And that's because, this true online TD lambda algorithm, we can only actually compute an efficient algorithm like this, where we have this easy way of updating the eligibility trace, in the case of linear approximation. There is this this algorithm which in theory can use it can use any type of function approximation with these gradients, but this algorithm, the way they've written it here, is we have to just perform a lot more weight updates, because you have to compute this truncated lambda return on every step. And actually, I think they mention here in the chapter how inefficient it is. But yeah, I think in general you have like, well, I'm not sure. I'd have to look at it again. But like, there's a reason why there's no pseudocode given for this algorithm in the chapter, and there is pseudocode given for the true online TD lambda algorithm, because in the case of linear approximation, there is a way to simplify the updates so that we have to do a little more computation than before. We have to keep track of, we have to do these two inner products, but really, this step in here, we just have to take this extra inner product of the eligibility trace with the feature vector, And, you know, other than that, this really has not much of a computational expense over the TD lambda algorithm. But, again, it only works for linear function approximation. So then, using this true online TD lambda algorithm, you can actually use this again, like you can define this for a tabular problem. And in the case of a tabular problem, each parameter would represent the number of states. And you can simplify this a lot because you don't actually have to take these inner products. Like here, you'll notice where I compute the value estimate and then the value estimate at the transition state. I'm just taking the parameter value at the state index. Here, this IS represents the state index. And that's because in this tabular problem, all of the states can be enumerated with a specific just numerical value because there's a finite number of states. And that's what I use for the random walk example. But you can see that, again, because this is an episodic task. So these episodes actually do terminate. So we don't actually need, like, by the time we're finished with an episode, we don't need to worry about the truncated return. We're going to be just using the full lambda return because we are going to the end of an episode. And that's why, like, the results here and in this diagram, that the online lambda return and like the true online TD lambda, should have the same results as the offline lambda return for this random walk example. They do. I mean, in my, like, this lambda value of 0.8 seems to be like the most efficient, at least over the first 10 episodes. But the whole purpose of developing these lambda estimates is ultimately to solve the control problem, where we're trying to optimize a policy and figure out the optimal action selection. Like so far, all of these estimates, this random walk example is just it's just a problem where the agent moves randomly from a center state and reaches an edge state. And this is just to show the accuracy of using this to estimate the true values. Right? But when we move on to the control problem, where like the simplest control algorithm we had that used sampling was the Sarsa algorithm. Originally the Sarsa algorithm had referred to, this state that, like, the fact that we have to look forward a certain number of steps to compute this target value. So here, like, the target estimate that we're using, because now we're approximating state action values rather than just the state values, right? Like for this algorithm, V, the state value function that we are computing here, is just a function of the state we're in. And now for the Sarsa algorithm, we now have this additional input value to our estimator, which is the action. And just like before, the reason why we want our estimator to compute to compute the state action values is so that we can look at a particular state and we can follow something like the greedy policy or the epsilon greedy policy, which will look at all the action values and then either choose the action value that appears to be the highest, which we had referred to before as the greedy policy with respect to the state. But now, because our estimator uses this, we can't actually have this target value that we're bootstrapping off of, which appears here. So this is now the TD error term, which looks very similar to before, but now the difference is we can't just use the state value, this S of t plus 1. We also have to have a sample of what action we're going to take at that state, because our value function is only defined for both states and actions as an input. we could, in the case of like using an expected update, like we had also seen in part one of the book, we could look at a distribution over future actions, but the simpler version is just we sample an action and then we use that. But this Sarsa lambda algorithm, what it's going to do is just use the lambda return. It's basically using the TD lambda estimate update. Here, like this is the eligibility trace update, and then the weight update. But now, the eligibility trace update is going to use the gradient of the state action values, not just the state values. But this Sarsa lambda, you can see like this diagram looks the same as the TD lambda algorithm. The only difference is now like it matters. We actually have to keep track of the actions that were taken as well. But otherwise, all the updates are very similar, except that we are now using this other form, the state action values, and therefore our parameters will have to represent some combination of the states and actions. Now, the way I had done this, well, you can start out in the case of having a tabular problem. I had said that we don't actually need like this state representation vector because we actually have a specific enumerated number for every state. And in this case, the way this Sarsa lambda algorithm is defined here in the books, right? They have this pseudocode for it in the book. So the book has one version of it, which uses binary features and linear function approximation. So here I have a few different versions of it here, including one that just directly works on a tabular problem, which is like this grid world problem here. So like this grid world is a typical toy problem from part one of the book, where each state is just a square in this grid. And then the goal, like when you actually reach this goal state, you terminate the episode. And you could set up this problem, like a typical setup would be to have a reward of -1 for every time step. So then, maximizing the reward would be minimizing the number of steps, and you have some function that would initialize the starting state here. So I did use, this is like some code from first part of the book. We hadn't really looked at this grid world example for a while, but I'll just show like here that this cartoon is just sort of showing this is actually showing what would happen, which states would be updated for a grid world problem where you only get a reward by reaching the goal, right? So you have sparse rewards, you only get a reward signal here. And if you do like one step Sarsa, then you only, at the end of the first episode, if all of these values start at 0, or all of the action values start at 0, then you only update the action value, which was the one you took right before reaching the goal. And then the more steps you expand it to, then you end up updating more of the values. And when we did the n-step methods, like the Monte Carlo method would update all of these values along the trajectory. And then for any value of lambda, depending on how large it is, now we will also update all the values along the trajectory, although, for lambda 0.9, for example, the values close to the start won't be updated nearly as much as the values close to the goal. But here's an example of like an actual grid world problem. And because it's a tabular problem, we can use the previous methods from the book to just compute the exact solution. So I'm sorry, I think this is actually missing. Sorry, I'll make this a little smaller so it shows more of the. Here. So this is showing like the path that the agent took under the optimal policy. Now, sorry. So this is the exact solution. Now, this problem, like in the first part of the book, we had these like windy grid world examples where you could have these wind values that would that would blow the agent up as it tries to move in a particular direction. So here, like if I set all the wind values to 0, then the problem's pretty trivial, right? This is the starting state, and the optimal policy is just to, walk right straight to the goal state. And here, there's no wind, there's no stochastic transitions. So, there's nothing to deflect the agent from this direct path. Now, this is showing the Sarsa lambda algorithm if we apply it to this tabular problem. And this is showing the steps per episode on average, so the lower the better. But this is a representation of how efficiently the agent is learning, or finding the optimal policy. And this is a pretty simple policy to learn, but still we're in the hundreds of steps here. We can see that the optimal number of steps is 6, because there's a reward of -1 per step. So here we can see that this is showing for different learning rates. This is like what we had looked at before as like a parameter study, where we have curves sort of exploring how the algorithm performs under different parameters. So here we're varying the learning rate, which we have for all these. The learning rate is sort of controls how fast the parameters are updated. And then lambda is what controls, how we're weighting the different n-step returns, right? So lambda is 0. This is the lambda is 0 curve. This is just TD0 learning. And, I don't actually have lambda is 1 here because the algorithm becomes unstable, but 0.99 is getting close to 1, and this is approaching Monte Carlo learning. And then, like for most problems, there is some intermediate value of lambda here. You can zoom in a bit and see that it's actually stable across a few different values of lambda. Here we get a pretty good solution at both lambda is 0.5 and 0.6. This is including like the early episodes where the agent is going to move around pretty randomly. We can see here that how close we're getting to the optimal solution. And then I can also make the problem like a little harder by adding these like wind values, which will deflect it. Here, I'll just put in some random values here. It does end up, the main change to the policy is that now the agent has to sort of loop around here to reach the goal. But the policy is still, involves stepping right, and then you just have to learn the right way to go around the goal state here. You can see that there's still these, a bunch of values of lambda that are all fairly close to being optimal. I guess I made the value of lambda that's optimal a little larger. Now we're getting a little higher to the Monte Carlo case, and that does make some sense. That as you make the problem more stochastic, that you might favor a little bit higher value of lambda initially, because the higher value of lambda, the less we're relying on bootstrapping. And the bootstrap values, especially early on, might be pretty bad if we have this like large amount of stochasticity in the environment until we get the estimates better. But again, like this parameter study is only for a certain time horizon of training. So it tells you like if you only have like 500 time steps to learn, then like this value seems to be like the most efficient, or this value of lambda. But it is interesting to note, like if you look at like this is actually the result for lambda is 0, and this is for 0.99, and you can see like how much worse these are than the optimal value of like 0.7 or something, where we have this huge drop off in efficiency at the extreme end of doing TD0 or something close to Monte Carlo learning. But so this is also this is another way of seeing like sort of how stable these intermediate values of lambda are. So here, like if I set this learning rate to like 0.5 or something. This is showing like a single training run. These results are averaged over a bunch of runs or 50 runs. So it's showing like the average performance. And here we're seeing the result of like one training run where this agent did learn how to reach the goal, although the path isn't as efficient as it could be. This is only training for 100 steps, or no, 100 episodes, sorry. So it is quite a bit more steps. But we could see that if we like made the lambda value 0 or around 0, here this is just redoing the training every time I adjust this slider. So this is like repeating the training with different low values of lambda. And you can see like the failure rate is pretty high. Like if the path looks like this, it means that the agent was unable to find the goal. So then if I go, more to what it seems like a more optimal value of lambda is closer to 1, go out here. And now you can see as I vary this, like these training runs are all, like they're all succeeding in one way or another. Like they may not, be perfect, but the results are certainly much more stable than at low values of lambda. But the nice thing about this algorithm is that we sort of have all the n-step methods available in the same algorithm. We just have to tweak this value of lambda, and we'll get them. And so we can sort of replace all the n-step methods we had with tabular problems now with this algorithm. But yeah, this is for the grid world. And then I believe I also have, oh yeah, so then this is also, there's also a version of this even for the tabular problem of doing expected Sarsa lambda. So I had already shown, if we go back, if we look at the Sarsa lambda code here for the tabular problem, right? We have this line here, here, where we're sampling the action, right, at the transition state. So this index here, this line of code is what computes the transition state. All right, so this is saying we were in a given state indexed by this IS, we took this action, and then we end up with this reward and this this transition state index. Now, if we haven't reached a terminal state, then we sample the action at the transition state. And then we use the state action value at both the transition state and the action at that transition state, right? And this is being used to compute the TD error, right? This TD error is being computed in a few different steps. Like this is the part where we take the reward and subtract the current state action value. And then this is adding the discounted value at the transition state, right? So this is how Sarsa lambda works. Now, this is, again, for the tabular problem. Now, if we compare it to, the expected Sarsa lambda, it's mostly the same, except now the difference is this function is going to compute, or it's going to fill this action value vector with all of the action values at the transition state. Here, I mean, this function that fills the action values is pretty simple. Here, all it's doing is grabbing the state action values. Right here, like the state action values are just a matrix where, the rows represent actions, the columns represent states. So this is basically grabbing a column from the state action values. And that column represents all of the action values for that particular state. And then we can use those action values to make an epsilon greedy policy. And then we can use, like, this epsilon greedy policy will then have, a probability of epsilon taking a random action and 1 minus epsilon of taking the greedy action. And then instead of just using, like before, the state action value at this transition action, now we're going to loop over all the transition actions and multiply it by this value, which is the probability of taking that action under the target policy, which in this, usually for expected Sarsa, like the target policy and the behavior policy would be the same because we're doing on policy learning. So that's really the main difference. Everything else in the algorithm is the same. There's just this extra, machinery needed to compute, to fill in these action values. So then this parameter study is just showing the result on the grid world problem of doing expected Sarsa. And I'm trying to see if this is the same number of steps, or to compare it to this. Here, let's just go back to this parameter study. We can see now that I've added these wind values, now, the optimal policy expected number of steps is 11. These seem to be, there's, a bunch of curves that are getting pretty close to basically like a value of 18. And for this tabular problem, the expected Sarsa results won't be that different. We can see the results are a little bit better. Like, it's like 17.5 instead of 18. And maybe it's a little more stable around multiple values of lambda. But, the more stochastic the environment is, the more benefit we'd expect to have from this, because this algorithm will reduce the variance of selecting the action on the next step. And then, because this grid world, like the states are actually, like the episodes are terminating, it's not a continuing problem. We wouldn't expect the true online algorithm to really be much different. This is just, this was Sarsa lambda, right, where we had taken the TD lambda estimate and converted it to a control problem by learning action values. The true online Sarsa algorithm is just the same exact idea, except now instead of using the TD lambda parameter update, we're using the true online lambda parameter update. So that's why this is called true online Sarsa lambda. But of course, this again only works for linear function approximation. So the only version of the algorithm here is for that. Whereas Sarsa lambda, here they're only showing a version of it that works with linear function approximation. But if you look in my notes here, I showed the version of the algorithm that's for a tabular problem, which is linear. This is the version of the algorithm that uses binary features. So for binary features, the thing you need to define is a function that gets the active features for a particular state. So here it's like if we initialize a state S, we have this function which will produce the active features, which then we can iterate over the active features. Like here, I have, so this function that does the action selection, this goes through the active features, right? And it only adds the parameter values for the active features, which is it's the same as doing this inner product, but instead of actually having the two vectors that we're doing the inner product over, we're just summing the parameters at the active features, right? Because the active features, they just have a value of 1. So it's pretty simple. There's no point in actually, having that whole vector available. But, for the true online So this is the expected Sarsa, yeah. And then for the true online version of Sarsa, here, this is the tabular version. But if you compare this to the true online PD lambda, those are the types of parameter updates that are happening here. There's just additional things need to be computed here. The eligibility trace update is different. But we wouldn't expect for this problem the results to be much different. So here is the parameter study. It looks about the same. You can also do an expect, yeah, so this is actually, these results actually do appear better for some reason. But what I had said about doing the expected update, that also applies to the true online algorithm, because the only difference in the expected update, like expected Sarsa lambda, is really at this point in the algorithm where we compute the delta, where the delta is we're looking at the action values at the transition state. You could do this same exact thing, like here, if we look at this true online Sarsa lambda algorithm. Here, this is the version without the expected update. So here, Q prime is using X prime, which is using A prime. To convert this into an expected update, what you would do is you would go through all of the A prime. So instead of here, choose A prime according to epsilon greedy, you would get all these epsilon greedy probabilities, which are going to be, it's just the probability epsilon of taking a random action, and then one minus epsilon of taking the greedy action. And then instead of having a single value here for Q, you would add up all of these inner products weighted by the probability of the epsilon greedy policy. But everything else in the algorithm would be exactly the same. And that is what, sorry, I'm showing here. And just like before, how, we had regular Sarsa lambda, the best result we get is 18 steps here. Then the expected version of it, we can see it's a little better. And then for the true online, it appears that for the true online algorithm, the expected version seems to benefit more from the expected update. Here we can see now it's quite a bit better. It's almost like 2 steps better. And the value of lambda is also quite a bit smaller. Like here, the optimal is 0.5, which is again relying more on bootstrapping. And that's another maybe pattern that we would see in other problems, where here, like, let's see, the best result, 0.6, 0.7. And then for expected Sarsa, yeah, it appears to be the same here, where for the expected update, we favor a slightly lower value of lambda, which is relying more on bootstrapping, because we're being less harmed by the random sampling of the action. So, this is for doing a tabular problem. I wanted, the other example they look at in the book was this mountain car problem, which we had done. Sorry if this, in chapter 10 of the book. Sorry, my web browser is being a little slow. But I can go back to it here. Also, just to refresh you on the mountain car problem. So, this was one of the first problems we had looked at that required function approximation. So here, we're assuming that we have a car that it's in this, this valley. And the state of the car is going to be its position and velocity, where the position is, it's bounded between negative 1.2 and 0.5, and the velocity is bounded between negative 0.07 and positive 0.07. I mean, these constants are just to make the particular physics of the problem make sense. And the possible actions are to either accelerate, reverse, or go with zero throttle. So depending on what the throttle is, we have this update rule. And this is like all the physics is simplified. But the point of this problem is you start kind of close to the trough of the valley here, and simply accelerating forward, it is not possible to get out. And I had shown this. This is again my notes from chapter 10, but this is showing like what happens if you just either accelerate or decelerate in this problem. You just oscillate back and forth in the valley. And then we had found that, if you applied the techniques that we had available back in this chapter, we had just done semi-gradient Sarsa. And here we show, these are some of the results in the problem, but this is pretty close to what the optimal policy would be, where this is showing a phase diagram of the position and velocity under the optimal policy. And this is showing how the position varies with time, where you sort of accelerate forward a bit, you get a little up this hill, then you go full throttle backwards to get further up the hill back here, and then you have enough momentum to finally make it over. So the most efficient solution just involves going forward and backward once, and you could be a little less efficient, but this is also what the value function looks like in the phase space of the problem, where the optimal solution sort of follows the gradient here of the value function. You can sort of see how this path mimics if you were to map it on to the value function, this would sort of step to increasingly higher values as we reach the goal. But then here, like this is an example of one of the solutions we had with tile coating. Again, like tile coating was a form of linear feature construction where the idea is you sort of define the size of the tile, usually as a percent of the maximum. Like tile coating can be used in a problem where the state is some like tuple of numerical values. So in the case of the mountain car problem, right, our state would be like this. Or sorry, no, this is an example of the position. Our state would be two values where one is the position, one is the velocity. And this is the range of both. It's like negative 1.2 to 0.5, and then this range. So the idea in tile coding is that we break up this numerical range into some number of tiles, and then we sort of tile the space and we shift and we have offsets so that whatever point you are in the space, there is some number of tiles that you're in. And this is showing an example in one dimension where the state is just this, numerical value from 0 to 1,000. And then depending on how many tilings we have, like here I have, 5, 6, or if I go up to like 10 tilings. So the number of tilings is for any given state, how many features are going to be active. And you can see here how as we move across the state space, we sort of change in chunks which tiles are active. And the size of the tiles is sort of how granular you are at dividing the state space. So you can sort of see here for the solution, the way this is kind of blocky. This blockiness is defined by how the tiling was done for this problem. But this solution is showing a case where we have 12 tilings. So, or sorry, no, 8 tilings, but 12 tiles in each dimension. The combination of the two ends up telling you how large the parameter vector is. But we had, so you could see like this solution, this is one of the Sarsa solutions. This is not Sarsa lambda, like this is semi-gradient Sarsa, which is always using a value of lambda equals 0. because this is like the simplest version of the algorithm that we had. We can see, you know, this is an example of the training process. It did solve the problem, but you see how it's less efficient than the optimal solution, how we are actually looping more than once around here. So if we go back to chapter 12 and we look again, actually, I'm going to first show the tile coding. So here I have this version of the tile coding. What it does is it ends up returning this get active features function. So rather than actually producing a vector of what the tiling is, it just returns a list of indices that can be used. And then this is, you know, the number of features, which is also needed to construct the parameter matrix for this problem. So what I'm showing here in this example, this solution method, go back to here, is using the same exact tiling setup as here. Okay, and it's the same exact problem. We can see from like the optimal solution that the best we can sort of do is around, you know, 120. Yeah, this is sort of an approximation to the problem, but you know, somewhere around like 100, you know, give or take 10 or 20 steps is about what we're aiming for. So now this is showing a parameter study for the mountain car problem using Sarsa lambda. And I'm using an exploration parameter of just 0.01. So we zoom in a little bit. So this is just showing like the simplest version. This is Sarsa lambda over 50,000 steps. This is the tiling parameter. And this is just defining the range of lambda and learning rate I'm evaluating. But we can see that what we were doing in chapter 10 was this blue curve, right, which is TD0. And this curve, this would benefit from a higher learning rate, but you can see that, you know, these results are also dominated by, this is just a measure of how quickly it's learning the optimal policy. So we can see it might get, I mean, clearly this algorithm is working. Like it's not going to finish the task in 200 or so steps by just moving randomly. In fact, I had shown that in this chapter that if you do just move randomly, you don't expect much success. I mean, here, like, it certainly doesn't finish in 200 time steps. I think, yeah, here's an example of like, this is sort of the average number of steps you would expect if you follow the random policy, and it's, you know, tens of thousands of steps that you need to finish instead of, you know, a couple hundred. So if we go back to the parameter study and zoom in a bit, we can see that, again, like this particular problem really benefits from a lambda much closer to 1, where we're almost getting to like a Monte Carlo method, right? Even like the Monte Carlo method actually performs way better than the Sarsa, you know, with lambda equals 0. And the result here is pretty good. I mean, this is already showing that we're already spending quite a few episodes very close to the optimal policy. So that's this algorithm. Now, again, like this problem is actually a deterministic problem. Like this is the rule of how to update the state. And there's actually no randomness here. The problem will appear a little stochastic from the perspective of the tile coding because we can't represent the states exactly, but that's really the only source of randomness here. Like we actually know exactly what the transition looks like, right? Because like the reason why it looks a little random with tile coding is like if we look here at what the estimate looks like we only know about the state we're in, this sort of blocky information about the state. So we don't know exactly what state we're in, therefore we don't know exactly where we'll end up with this transition. But that's a pretty minor source of randomness. Like in general, this problem is not. So I would not expect the expected Sarsa to have much of an advantage over the regular Sarsa. I mean, we can zoom in a bit and see the results are basically the same. I mean, if anything, it's a little worse, but that's probably just from, the randomness of the trials here. So we can see like the best result, also like the value of lambda with the best result is unchanged. So like, qualitatively, these are about the same results. We have this value of lambda that's pretty close to 1, but it's working pretty well. The other thing that I had done in this problem is that, because this problem is deterministic, like we actually know the exact form of the transition, we don't actually have to learn action values. We can actually do something which is sort of a dynamic programming version of the lambda return, where we only use the state value estimates and we reconstruct the action values from the state values. And well, before I show like some of exactly how that works, we can see how these results are actually quite a bit better. This method, the way I've done it, is also, it's a lot more efficient in terms of the number of parameters, because the way I'm representing the state action values for this mountain car problem with the tile coding, if we look at so this is for binary features. This is like the true online Sarsa lambda algorithm. And the parameters here are a matrix. And the reason why they're a matrix is that each column of the matrix is the dimensionality of the feature vector, like how many features there are. And then that's each column. But then each column also represents an action. So when I want to get the action values here, I don't actually have a separate feature representation for the actions. What I have is just an entirely new set of parameters for each action. So like each action is just its own set of parameters. And I found there's to have more success actually doing that than what they do in the book is actually a little different. I think it was mentioned. It's mentioned in one of these chapters when they talk about linear approximation. They definitely show it in chapter 12. But they have this function here, this x function, right? And this x function returns a feature vector for the state action pair. Now, instead of doing this, what I'm doing here is there is just an x, like a feature vector function for the state. And then for each state, like for the parameters, instead of doing this inner product here, what this does is, like here, the weight vector is a vector, but the length of the vector represents the representation of the state action pair. In my version of the algorithm, the parameters are a matrix, and the x just represents the state, but then the q value comes not from changing the state representation with the action, but from just grabbing the set of parameters that represent that action. Right? So I'm keeping all the actions like isolated. And part of that is also because these problems all happen to have a finite number of actions. So I can always separate the parameters in that way. None of these algorithms we've covered so far actually handle like continuous action spaces, which is why you can see whenever an action is represented here, it's always represented by an index of some kind, because the actions can always be represented by an index. So for the dynamic programming, the comparison to this method is that when I use this algorithm, we're actually back to computing these estimates, just the value estimates here, right? Where here we were computing state values, right? We had moved on to computing state action values to do the control problem. But if you have a deterministic problem like the mountain car problem, you don't actually need to compute all the state action values. You can reconstruct them later, which I have a little like summary section which shows how to do that. But this is just showing the result of doing this parameter study. Everything is the same. The state representation is all the same. Like all the tile coding is the same. Because remember, like the tile coding was only being used to represent the state. The actions were just all considered as a discrete set of parameters. So the actual value of lambda is the same. That's optimal of this 0.96. But we can see the results are better and also seem to be better across a wider range of learning rates. But this method is also simpler because I'm using what's known about the dynamics of the environment to compute the action values. Whereas in these methods, you actually have to wait until you've seen a particular action value sampled before you update the parameters associated with that action value. Here, there is just a single set of parameters for the state. So I'm making the job of the function approximation a lot easier because I'm not actually requiring it to learn all the action values. Now, you can also solve the mountain car problem with the true online version of all this stuff, which again, because this problem is episodic and it does terminate, you wouldn't expect much benefit from the true online Sarsa lambda. Here, these results seem to be a little better. Right here, we had like 162. Here, the average is 160. And then again, like the expected version, we wouldn't expect much change. Yeah, again, it's like not really much different because the problem is not stochastic. So we don't get much benefit from the expected update. What does give quite a significant, even additional improvement is this is now doing true online Sarsa lambda. But again, I'm sorry, not Sarsa lambda, but the dynamic programming version of this, right, where it's the same thing I showed here, like dp lambda, but here this is dp lambda with the true online version of it, right, which again, like the true online version is the version that always computes the truncated, like the n-step truncated version of the return, which is like as far as we can go before we have to truncate it, right? So like at whatever step we're on, it's going to do the estimate up to that number of steps. So in theory, it should be better. Of course, we have to use linear approximation. Luckily, this tile coding technique is a linear method, so we can use it. And if we combine that with the dynamic programming version of this algorithm, it seems to give even more efficient results. Like here, I mean, again, like the learning rate is much smaller here. And I mean, we're even at a higher value of lambda. Like here, we're getting almost close to the Monte Carlo return. But this appears to handle, the data along the way of being in an episode much more efficiently. Like this is already, I mean, this is like including what could be like a 10,000 step first episode in this. So even this average is actually better than like this Sarsa solution I showed. Like this is the final solution of this iteration of Sarsa training. And we can see that this still is taking, around like 160 steps to finish. And this is showing this version of the algorithm, over the first, 50,000 steps, which is including like the bad part of the training where it's not even close to the optimal policy, is actually averaging with an even lower result than that. So, there appears to be, this is sort of like, I guess, like, so far, from what we've learned so far, this is like a kitchen sink approach where we're using like the best version of the Lambda return update and taking advantage of knowing the dynamics of the problem. And then we seem to get the best result, which is, at least it's showing that our algorithms are, are working properly, or like there's some reason to do this true online version. But I have sort of for the on policy methods, this chapter like throws a lot of different things at you. So I sort of tried to summarize it a little bit here. But for the control problem, we had, Sarsa lambda and true online Sarsa lambda. And for episodic problems, these approaches should be very similar because by the time we finish an episode, both should be the same as the offline lambda return. This might, no, like I believe it. Yeah, notwithstanding that there is a slight difference with the value function changing during an episode. And then with Sarsa lambda, we could use any type of a function approximation because the eligibility traces we were using could just use the gradient. So as long as we can compute a gradient of the function approximation, we can do this. This algorithm, we had to use linear function approximation to take advantage of this. And then the other sort of variable that we can play with is how we compute the target value. So usually when we use state action values, the reason why we do that is so that we can just look at the state action values and we can figure out the greedy action or the epsilon greedy set of actions. And then this is the one-step TD error that we would usually use, where we would sample that action, right? And we would use that as the bootstrap value. What I was mentioning of using the expected value instead is that we look at this, if we're using the epsilon greedy function, like here we actually sample A prime with the policy. Whereas here we have the probabilities. Wait, there's a little, all right, let me update this. And then instead of just using this single sample, we sum our approximation function at all of the action selections weighted by the probability. And the purpose of doing this from all the earlier methods was to reduce the variance of the update. And in a lot of cases, we might as well just do this because we do know what these probabilities are. So there's no point in wasting them. And we can also do sort of a version of Q-learning when we do this, where we can actually have a different target and behavior policy. But that's, so far all of these are on policy methods. So all the expected versions would use this type of expected update. And then the final thing I mentioned was the dynamic programming alternative, where if we know this probability transition function, then we can compute state values instead of the state action values. And then I didn't actually write the formula down here. I can add it to the notes, but we can use these probabilities then to say, if we're in a given state, once we select an action in that state, we know all the transition probabilities. And then we can use the bootstrap value v hat of S prime to figure out, we can derive what these Q hats should be, right? So this is like we use this in combination with the state values to derive these values. And the advantage of doing this is that, we make use of the information here. We don't need to have a separate value estimate for each action. The only thing we have to worry about is making sure that the state values are accurate. And there's no expected version of this, because again, like when we look at the TD error for this method, we are just going to use v hat of s prime here. We don't have to worry about what the action selection is, because the reason why we have to do this and sample here is because we can't just use all the state action value estimates. Like we have to actually know what action we selected based on the policy. And here, the state values are already going to be the correct state value estimates given whatever policy we're following. That's already sort of baked into this algorithm. So again, like this is not really mentioned in the book at all. I don't think there's any example of a non-tabular problem where we actually use the probability transition function. But you can do it. I mean, and there are a lot of cases where you might have like an intractable state space where we can't list all the states out. But if we do have a given state action pair, we actually do have pretty good information about what the transitions look like. So I found that, actually solving these problems, if we go back, when I had done this mountain car problem, I also, here, this is the dynamic, yeah. So I had done the same sort of dynamic programming method. And you can see like you have to tweak with like the learning rate and the parameters a bit. But you can see here that like the value function being learned here is actually much more accurate to the true value function than, like this did solve the problem correctly, but what the value function should look like is something more like this. And the dynamic programming version, it just makes much more efficient use of the samples. And the longer I would train this for, it'll get much closer to an optimal policy. And you can even use the dynamic programming solution with nonlinear function. Like this is an example of from before of using a neural net approximation for this problem. But yeah, so I think, I mean, that does like finish sort of the main control problem solutions. I didn't reproduce this chart exactly, but in the book, they have a comparison of different methods showing the true online method to be the best for the mountain car problem. And I think I did find basically the same thing, right? This was Sarsa lambda. The comparison here would be, this isn't showing different values of lambda. This is like they've already selected for every learning rate the best value of lambda here. But yeah, this is showing the true online solution is slightly better here than the Sarsa lambda solution, right? And then even better than this, is which isn't shown in this chart, is the dynamic programming version. So the remainder of the chapter deals with just more elaborate things that you can do with a lambda return, including off-policy methods, and then ways to make those off-policy methods stable. So maybe we'll touch on that a little bit next time and conclude the section. I mean, even the first part of this chapter so far is already a little dense and complicated with a lot of different techniques. So I don't know how much interest there is in going over like all of the off-policy variations of these as well. But, we already have quite a large family of techniques, just going through like these different options. But yeah, the off policy method sort of introduces a version of Q learning that uses eligibility traces and keeps it stable. So it might be worth looking at. But the next chapter is really completely different from this. It's the final chapter of the part 2 of the book, and it covers policy gradient methods. So it would be a little weird to do the end of chapter 12 with policy gradient, but I don't know. Another option is to, I guess, do a few more example problems and do more like parameter studies on something beyond just the mountain car problem. Here they just sort of threw in a diagram of different different example problems, and yeah, off policy methods. And yeah, because I think the remaining exercises also are a little tedious and mathematical, and I don't know how much value there is in going over them like together, unless someone has a particular question about how to solve it. So, yeah, I don't know if there's does anyone have any feedback about what section to do next, or how much more of these techniques to cover? Or any question at all? Because yeah, if not, I guess we'll finish up there for now, and then I guess I don't know. I guess I'll just decide what to do next time. I probably will maybe finish some more of this chapter, maybe reorganize or clean up some of the notes from before. Uh, could you tell us? I don't quite understand your question. You mean, I mean, the mountain car problem there were sort of different solution techniques used for it, and it is just like an example, like a toy problem. But do you mean like what are other problems similar to it?
Like, where does it get applied, right? Like in the current scenario, let's say in a real world use case, where do you think this might get used?
Well, I mean, in a real world use case, like, I mean, it depends on what the real world application is. Like here, this problem is very simple. Like these two lines define the dynamics of the problem, and this is not like realistic physics at all. But you could make the simulation more complicated, and you could have much more complicated dynamics. Like you could have different shapes, a map, like this car could represent some kind of robot where it had additional actions. And then the goal of using these techniques would be to sort of estimate a good policy for the robot with some dynamics assumptions and some map assumption, and then you could see how it maps on to the real performance. But I guess I didn't show like here, like what's being shown here at the end of the solution, like this is the value function learned, but really what you care about is the policy function. So this is showing, like, depending on the position and velocity of the car, what the policy is. And like blue represents like deceleration or negative throttle, red is positive throttle, and then gray is no throttle. These green lines are showing what action the agent is taking. So, the goal of any of these things is to sort of estimate a policy and then actually apply it to something. If this whole thing is virtual, where you're actually trying to find like the optimal behavior of something that itself is going to function in a simulation like this, then you can actually, like, the optimal policy will actually be what you want to use, because there won't be this like simulation gap between the model and the environment.
Got it.
But you know, this policy function is sort of the goal of all of these problems. It's just that what the actions are, what the states are, and the dynamics are what changes. But you know, you can represent a lot of different real world problems as, you know, one of these Markov decision processes where you have like some state space and then some way of transitioning between states.
Got it.